So the first thing I'm going to be covering here is how we program 4-axis wrap programming methods. Now some systems they call it wrap machining, where you just have to have the geometry that you're trying to program just laid out on a planar surface like your XY plane, as you can see right in here. So here I'm going to be first illustrating how the wrap and unwrap works in CAD, and I'll also talk to you about how it's handled in the CAM programming side of it. So typically in your CAD application, you can use the wrap and unwrap feature to wrap geometries onto a surface in here. So here I have a bunch of curves modeled in here, and I'm working inside of Rhino. So I'm going to show you how we could wrap these curves onto the surface. So in Rhino, you can go to curve from objects and use what's called apply UV curves. And now I'm going to select all of these curves in here that needs to be wrapped onto the surface. I'm going to select the curves, and I would like to wrap it onto the surface over here on the top. So I selected it. You can see that the curves are now being wrapped onto the surface. So the way we handle the programming of 4-axis toolpaths, the wrap method toolpaths, which are 4-axis facing, pocketing, and profiling, is you would actually be able to select the curves directly off the model surface itself. You could select them. So once you select these curves, when the toolpath is being computed, it initially unwraps it, similar to what you see here, onto a planar surface or onto a plane. And then once the toolpath is computed, it wraps it back. Now in some of the other systems, you would actually have to just select them in an unwrapped format, but the nice thing in our CAM product is you're working with directly 3D geometry, so you could select the curves or surface edges directly off the 3D model, and the CAM part of it will take care of performing the unwrap, computing the toolpath, and wrapping the toolpath back onto the surface. So we wanted to give you a true 3D representation of what you're actually going to be programming, so it makes it easier for you to also visualize the same thing in the simulation process as well. So you would be able to directly select these curves as your part regions when you program your toolpaths inside of Rhino CAM or Visual CAM, or even Visual CAM for SOLIDWORKS. You can directly select those curved geometries as your part regions for programming these toolpaths. So I'm going to now show you an example of how this is being done in the CAM. So here what we looked at is how the wrap and the unwrap technique works in CAD, and also we described to you how it's done in the CAM side of it. So now let me go ahead and bring in an example in here, and we'll program a toolpath that would involve wrapping and unwrapping in here. So the first part I'm going to look at is called Band Design 1, and I'm going to go ahead and load this part in here. As you may also notice this part in the presentation slides. So here you can see that the part has pockets, and these pockets have been actually modeled into the solid model itself. Now you could have it modeled, or you could just have these curves wrapped on these surfaces. You really don't need to have the pockets designed into it, but if you have it, that's great for visualization and for your simulation purposes. So we have these wrapped onto the surfaces in here, and now we're going to go through the process of programming it. The first step is you go into your milling browser, and under the machine tool setup, you would like to make sure that you have your number of axes set to 4, and also your configuration. So we're going to be working with rotary tables where the part can be turned. So we have the configuration set to a table right in here. And you also want to make sure your rotational axis is defined. So typically in 4-axis, you'd either be defining your rotary axis either along X or Y. In this particular case, the part is oriented along the rotational axis on the X-axis direction, and we've set it to X. So make sure you orient it according to how your machine tool is set up. So most machine tools, the rotary axis could be on the X-axis. On some machine tools, they could be set up on the Y-axis. So you need to reorient the part as needed and establish your rotary axis and the rotation center. Now in the next step, we would want to define our stock in here. So I currently have a predefined blank for the stock, where this stock blank is hollowed out, and I have it created and saved in a different layer. So I'm going to make that layer visible in here, and I'm going to select the object, which is our blank right in here. As you can see, the blank is basically just like a tube stock. So I'm going to highlight this and go to stock, and choose stock from selection. So now the stock is being defined, and I will go ahead and hide the blank. And as you can see here in the Simulate tab, your stock blank is defined. So we did a stock by selection. The stock from selection is offered in Pro and Premium configurations. If you're using Expert configuration, you would be able to define it as a cylinder stock as opposed to stock from selection to run the verification. So you could do a cylinder stock where the stock would basically be just a solid cylindrical blank as opposed to being hollowed out on the ID. So once you have the stock defined, in the next step, you would like to program our toolpaths in here. So I would like to program these pockets, and I'm going to program them in 2 different operations using 2 different tool types in here. So to program them, the first step I'm going to do is go into 4-axis, and I'm going to choose pocket machining. So these are similar to how we program pocketing, profiling, and facing in 2-axis, but these are wrap methods like we talked about just a few moments ago. I'm going to use pocketing in here, and in the 4-axis pocketing operation dialog, I'm going to choose select curve regions. Now these are the part regions I'm going to be selecting for machining, so I'm going to go ahead and select these curves around the edge of the part. Now I could be selecting curves, or I could be even selecting surface edges from the model. So if you have multiple curves or surface edges, you could select them from the part directly as your part region or the drive geometry for programming these features. So I have these parts selected. Now to make your selection process easier, you could use select by layer, select by color. If you have these pocket regions assigned in different colors, you can take advantage of those selection techniques available in the host CAD system, which could be Rhino or it could be Visual CAD CAM. So I have all of these regions selected right in here, all of these 7 curve regions selected. In the next step, I'm going to go to the Tool tab to make a selection for the tool, and I'm going to be using a 1mm ball mill to program these pockets, since these are fairly small sized rings. And I'm going to go into the Feeds and Speeds tab to load the feeds and speeds from the tool. And then in the Clearance tab, you'll notice that the clearance is defined as a clearance, cylinder clearance. You could choose automatic, or you could even specify stock max plus a radius. In this particular step, I'm just going to use a 2mm radius around the part, so the clearance would be 2mm above the cylinder, above the stock of the part cylinder in a definition. And then I go into the cut parameters where I could specify the global parameters. These parameters are defined very similar to how you've done in your 2-axis pocketing operation. You establish your tolerance, stock, choose your cut pattern, your cutting direction, establish your step over, and then you can specify your cut levels in here. So you can specify the total depth of cut, and you can specify your rough depth and depth per cut in here. So I would like to break this up into 2 passes. And I'm going to split it up into 1.35 millimeters per cut. And these are basically radial cut levels that you're looking at in here. And then you can also establish your entry and exit for pocketing, and then pick Generate. So the pocketing toolpath is computed. So as we talked about here, the curves are unwrapped, the toolpath is computed, and then wrapped back. So everything is done automatically, and you can see how quickly the toolpaths were generated, and all of the computation is taking place within a very quick amount of time here. So the 4-axis pocketing toolpaths are generated, and also your rotations are automatically computed. The degrees, the angles are automatically computed. So when we post-process the toolpath, you'll be able to take a look at the posted output, which shows the angle values as the part is being rotated on the rotary axis. And since I chose depth first on the cut levels, the pockets are basically programmed to the total depth before it goes from one pocket region to the next pocket region. As you can see, there's 2 levels being programmed on each of these pockets. So parts like these can be programmed for, toolpaths like these can be programmed for parts that have a constant radius. And for the wrapping and unwrapping, the system computes based on the radius of the part. So the radius of the part geometry is known, and that's basically taken into account for wrapping and unwrapping. So if you have parts that have a constant radius, like bands or rings like these, you could use the 4-axis wrap methods, which could be 4-axis facing, 4-axis pocketing, 4-axis profiling. Now the projection method we talked about in the first webinar which is 4-axis parallel finishing, can also be used for parts that do not have a constant radius, like the ring models we looked at earlier. So for 4-axis facing, pocketing, and profiling, we would be needing to have parts that have a constant radius on these. So there's the simulation of these pockets as you're seeing it. And again, folks, if you do have any questions, you're welcome to post those questions in the questions panel in your GoToWebinar, and we'll try to get those answered to you. So once we have these pockets programmed, I would go back and program the next set of pockets using a taper tool in here, since there are some tighter areas which I can't get to with a ball mill. So to make my workflow simpler and easier, I'm going to make a copy of this operation, right-click and copy and paste it. And now I'm going to modify these, remove my current selections, and go ahead and pick the other regions right in here. And you can use your control key to drop a region that you do not want it to be selected if you accidentally selected it. So I'm going to select these regions right in here as you notice it. Or I could be using select by color if I had them assigned to different colors. Or I could also use select by layer, or use one of the other selection techniques that are available in Rhino or in Visual CAD. So I have all of these regions now selected. I'm going to swap my tool to a taper tool in here, and leaving all the other parameters at the current settings, select generate. And this would create the pocket toolpaths for the other features that are on the model. Again, it uses the wrap and unwrap. So it unwraps the geometry, creates a toolpath, and wraps the toolpath back onto the model. And there's the pocket toolpath being programmed with a taper tool or a conical tool. You could always select pause and then pick simulate to end to run through the simulation. At this point of time, I'm just going to hit pause so that we can go and cover some of the other topics in here in today's webinar. So again, once you have these programmed, we could switch back to the program tab and then post-process the output. So I'm going to right-click and post. And for the post processor, I could be selecting a post that's applicable to my machine tool. And I'm just going to go pick a FANUC control in here. I can select the post from the list and select post. And the posted output file would now show up in a text editor, which could be a notepad or text editor of your choice. And as you can see here, the rotation angles are automatically computed and output in degrees. So you wouldn't have to manually compute or index them. They're automatically computed based on the curved geometries that you selected for programming your 4-axis toolpaths. I'm going to go ahead and save this file out. The next thing we're going to take a look at is how we could program a 4-axis profile toolpath. So you could have a band design, a ring design you could be using, like for features like these on the part right in here. I'm going to use a similar process to program it. So I'm going to first start out by defining a stock blank in here. So I have it on a layer. I'm going to just highlight it and use stock by selection. I could do a stock from selection, so there's your stock blank that's being defined. Now, if you're using a standard, the expert configuration where you can do a stock by selection, you could just do a cylinder stock in here and use copy model bounding cylinder. It would define it as a cylindrical blank. So you can see the hollowed out stock, but you can still use for the purpose of verification or simulation. Now, since I have a stock defined in here and I have access to the Pro and Premium configurations, I'm going to do a stock by selection. And I'll hide the stock blank that was modeled in the CAD. So we now have this part in here. As you can see, the part has these profiles cut out on it to create a pattern on both sides. Now again, this is a band with a constant radius, and I would like to profile cut these shapes around the part. I have 4 of these on each side. So the workflow would be very similar to what we did in the previous example. Instead of using a pocket operation, here I'm going to use a profile operation. Again, go in 4-axis and choose profiling and select these curve regions. You could select them by layer, or you could just graphically select them. You can be selecting either a surface edge, or you could be selecting a curve to make a selection process. In the next step, make a selection for the tool, and in this particular case, I'm going to use a 1/8" end mill, establish feeds and speeds, and you can establish your clearance. In this particular step for the clearance, I'm going to just put it 100 thousandths above the stock max. In the cutting parameters, you can establish a cutting direction, whether you want to climb mill, conventional, or mixed. I'm going to use mixed cuts. And for the cut start side, you could choose right or left for the cut start side. And since I need to program a larger cross-section area here, I'm going to use the total cut width in here and specify a total cut width of 100 thousandths, and we'll use a step per width of 50 thousandths. So I would like to step it over in 50 thousandths passes and start 100 thousandths away from the edge of the part. And then in the cut levels, I could specify my total cut depth. This would be your radial cut levels. This would be 100 thousandths, and I'm going to basically split this into 2 passes. So I'm going to go slightly deeper to clear the material. So I'm going to change it to an 1/8 of an inch, and we'll split it up into 2 levels of 1/16 of an inch each. And you can also establish your entry and exit parameters in here to how you want the cutter to lead in and lead out. And this is very similar to what you've seen in your 2-axis methods, where you can specify your entry and exit options. Very similar to 2-axis profiling, and you could apply entry and exit for each cut level. So again, it does an unwrap, computes the toolpaths, and wraps it back. And there's your 4-axis profiling toolpaths. Now let's go ahead and run a verification. We'll switch to the Simulate tab and select Play. I'm going to slow down and rerun the simulation. So if you want to slow it down, you can use these slider controls. In addition to that, you can go back into Simulation Preferences and use Simulate by Distance and specify a display interval value to further slow down the simulation. So there's the profile cuts in 4-axis, and by specifying a total cut width, you're stepping it over 50 thousandths on each cut. So we now program the profiling for one of the sides. We could go back and repeat the same process for the other side. So I'm going to copy and paste the operation. You could use Control-C, Control-V, or you could do a right mouse button click, copy and paste, and go back and reselect the geometries in here. So I'm going to pick the geometries over here on the other side. As I pointed out earlier, I could be selecting either surface edges, or I could be selecting a curve region. So in this particular case, I'm going to use a curve region, as it just makes it easier rather than having to pick multiple surface edges. Now you could use your curve extraction tools in the CAD program, like duplicate edge, duplicate face border, or other tools to create these curves, and then you can chain them or join them together and select them for programming your toolpaths. Now when post-processing these toolpaths, we now have the ability to output inverse time feed rates. So you can go ahead and enable the inverse time feed rates. If your controller expects a G93 or a G94, you can go over to your feed rate section in here, and you can enable this inverse time feed rate and select the code to toggle it on and toggle it off. So I believe G93 is commonly used for inverse time feed rate on. You can enter this parameter right in here, a G93, and a G94 is to basically turn off inverse time feed rate. So once you've established this, upon post-processing your machining operations, this would output your inverse time feed rates. As you can see, there's a feed rate being computed and output for each line of motion, each line of linear cut motion. So the inverse time feed rate is a new feature that was offered in version 2017.